Hi everyone, and welcome to another seminar of Physics Latam. Today we are very happy to have Bianca Dittrich to give a talk on quantum gravity and quantum spacetime in 3 dimensions. Bianca Dittrich is a physicist known for her contributions to loop quantum gravity and the spin-foam approach to quantum gravity. She received her PhD in 2005 from the Max Planck Institute for Gravitational Physics in Potsdam in Germany. Then was a postdoctoral research fellow at the Premier Institute until 2008, a Marie Curie fellow at Utrecht University until 2009, and a research group leader at Max Planck Institute for Gravitational Physics until 2012. Since that same year, she has been faculty member at Perimeter Institute for Theoretical Physics in Waterloo, Canada, and also an adjunct professor at the University of Waterloo. She is currently focusing on the large-scale behavior of spin-foam models. Once again, we are very happy that she has to give this talk for us today. And remember to raise your hand at any point if you have any question, and now I'll leave you with Bianca. Please go ahead.
Thank you, Daniel, for the nice invitation to speak here. And so I was asked to speak about quantum gravity. And quantum gravity, well, I would say in 4 dimensions, we don't really have an approach where we are all very happy with, and there are many open problems. So to give you a bit of a taste, I decided to present a bit what happens in 3D, because in 3 dimensions, you could say we have at least a theory which we could explore and where we can solve things, because as I will explain, 3 dimensions has peculiar properties which makes it much simpler to deal with than in 4 dimensions. Yeah, please ask questions. So I don't know you. I don't know really what your level is. So I guess it's more useful if you ask questions. I can a bit adjust during the lectures. And so there are these Psi lecture notes. So Psi is a master course at PI. Email me if you want to get a copy. They're kind of always non-finished, so it's in the draft stage. Sorry. So for me, the interesting aspect of quantum gravity is really that it's supposed to be a property of quantum space-time. So according to Einstein, gravity is encoded in the geometry of space-time. And so quantum gravity really should mean a theory of quantum space-time. And so that makes it so interesting as compared to, say, quantum field theory, because in quantum field theory, usually space-time is a given, whereas here you expect that really space-time should be affected. And a simple argument where you see this should be happening is based on so-called relational observables and the fact that diffeomorphism symmetry is a symmetry or gauge symmetry of gravity or of general relativity. So the observables in general relativity should have to be diffeomorphism invariant. And so these are very different observables from quantum field theory. And in quantum field theory, phi of x is an observable, but it's not in general relativity. So to really construct something which we could in principle allow, you need to construct reference frames. And so let's say we have 4 scalar fields or clocks and rods which are represented by 4 scalar fields. In that case, we can express what is the 5th field, psi, at the point where 4 scalar fields take certain values. And so this object would be invariant under diffeomorphisms, because if you apply diffeomorphisms, then basically all the points change, but the points in the f function change and the points in the phi function change. So that's supposed to, that is invariant under diffeomorphisms. So that's to say, in physical terms, to really do a measurement at some point in space, you always need clocks and rods to actually specify where this measurement is happening. But if you go to kind of, quantum field theory, particle physics, we need a very high resolution to look at high energy events or, processes which happen very near together. And as we know, we need a very high energy to get to this high resolution, to be able to resolve very nearby points. And so we would have to concentrate a high energy in a very small region. And so that is in principle okay, as long as it's quantum field theory. But if you bring general relativity into the game, well, we know that if you do concentrate an arbitrary large or very large energy into a given region, then we expect black holes to form. So once a black hole is formed, you actually shield this event, so you cannot observe it. So there's a very interesting mixing between UV and infrared going on here, which indeed, plays a role in a number of arguments. And you can kind of really make a more quantitative argument with a bit of theory and so on. And I've done it in some paper. So here that means that you should expect that the resolution is bounded so that you don't have a smooth manifold, but something else is happening. So space-time points and smooth manifolds seem to lose meaning in quantum gravity. And so possibly it should be, all these concepts should be replaced by something else. And I will present one 3D gravity, where we can go quite far in quantizing, and where indeed the result is something else than the smooth manifold. And to do so, I will just start with the classical basics. So I don't know if you know that, but that's to provide some background and basis for the quantum theory, which I'm then going to discuss. Okay. So for technical reasons, I will consider 3D gravity in an Euclidean spacetime. So it will be a quantum theory of Euclidean 3D manifolds or geometries. But I will put into the path integral an I. So that's different from so-called Euclidean quantum gravity, where you have where philosophically we rotate. So this path integral will be the weight over all 3D geometries, but the weight will be with an I, and this will be the Einstein-Hilbert action. And that would be kind of defining the path integral over continuum manifolds. Where this is the usual Einstein-Hilbert action. You might have seen that in 4D. It's a Ricci scalar, which is constructed out of the Riemann curvature, integrated over the manifold with the determinant of the metric. But in 3D, basically the action looks the same. So in principle, in a path integral, we want to construct this path integral, evaluate this path integral. Doing so, however, you have a number of kind of complicated issues to deal with. And the first one, which we will immediately address, is that here what you in principle should integrate over is only positive definite matrix, so a matrix with an Euclidean signature. But the space of matrix, so this will be 3-dimensional matrix, so there are kind of 6 entries. And usually if you just write these matrices, with 6 entries, you could say it's R6, but this would define all kinds of signatures. So this would this would not be a restriction over only positive definite matrix. On the other hand, this restriction over only positive definite matrix would be kind of, if you try to do it directly, hard to implement in the path integral. So even in quantization and canonical quantization. Another issue we would have to eventually to deal with is diffeomorphism symmetry. So this action is invariant under diffeomorphisms. Here there is kind of the path integral measure implied, and so this measure should be also invariant under diffeomorphisms. But that means, since diffeomorphisms are non-compact, you get basically the integral is constant in these directions coming from diffeomorphisms, and so you would expect infinities, or you have to gauge fix. Last but not least, so these kind of path integrals, I mean, in quantum mechanics, you learned some special cases that you can solve the path integral for the harmonic oscillator. But otherwise, we do not have really good techniques to evaluate such path integrals, particularly for field theory, where we have an I here. If it comes in particular to non-perturbative evaluation. So that's why Euclidean quantum gravity was very popular, but Euclidean quantum gravity comes with other severe problems, in particular the conformal mode. In Euclidean quantum gravity, you would have a minus sign, so it would be minus the Euclidean action, and you can do Monte Carlo simulations. But for Monte Carlo simulations, you really need a statistical interpretation, which we don't have here. Again, in 3D, that's something we can address because the theory is very special, but in 4D, that is one of the main technical hurdles, because it's very hard to compute like what these amplitudes are without having any techniques. Okay, so I mentioned, well, there's an interesting way to approach this first point. To make sure that we only integrate over positive definite matrix. And actually, well, it ensures that we integrate only over positive, you could say, semi-definite matrix, so there can be still degenerate. And so the trick is more or less that you express G, the metric, as a square of something. And so the square in this case is well, these objects are known as, well, in 3D, triad variables. So they're kind of triads. So they're again kind of six numbers. Mu and I go from 1 to 3. And okay, so it's a co-triad. And so if you define the metric in this way, that you here just contract this so-called internal index, G mu will be automatically positive semi-definite. So it could be that the determinant is 0, but otherwise the signature will be always plus, plus, plus. Okay, and the triads will be inverse to these co-triads. Having done so now we basically well, sorry, it's more than 6 numbers. So these matrices do not need to be symmetric. So these are actually 9 numbers, but now we have gone from the matrix, Spacetime matrix, which is 6 numbers, to 9 numbers. And in fact, what we have introduced is an additional rotational degree of freedom per spacetime point. And so if you look at this formula, if we rotate this internal index with a SO3 rotation matrix, the point is that these rotation matrices leave the Canonical delta, that's the internal flat matrix invariant. We would not change the spacetime metric, but the action is just a function of the spacetime metric. So this introduces an additional SO3 gauge freedom. And in fact, the nice thing about this formalism is that you can do that with Euclidean signature SO3, but you can also do that for Lorentzian signature SO21. So basically, whether you have an Euclidean theory or Lorentzian theory just depends on the kind of gauge group you are choosing, SO3 or SO21. And so for SO3, that is technically simpler because we know much more about the representation theory of SO3 and it's compact. Whereas for SO21, it's non-compact. And that's kind of, I think SO2R is a cover of SO21. So it's also a bit more involved, the representation theory, but in principle, we can do Lorentzian signature along the similar lines as here. I see there's something in this. Okay. Going on. So there's a bit challenge apparently to move a slide. Sorry. Seems my computer is broke down. Okay. So here I already spoke about the gauge group. And so indeed we can use a connection and in the end, the formulation of 3D gravity which we will have will look very similar to gauge theory. In fact, as I will say later, the quantization we will use is very similar to lattice gauge theory, and 3D gravity can be seen as a zero coupling limit of a lattice gauge theory. Okay. So to do so, what we do is to introduce a connection variable, and that allows to define covariant derivatives which can deal with this internal index j, which we introduced for the triad variables. So now any objects with respect to the internal index, so which use this internal index as a frame, we can parallel transport them. If we want this parallel transport to preserve the internal metric, which is a Kronecker delta, then we basically need these internal indices appearing in the connection. If we pull one down with the Kronecker delta to be antisymmetric. And so that is very nice because if we assume that we have an antisymmetric pair of indices, well, we can actually rewrite in 3 dimensions. So in 3 dimension antisymmetric pair of indices would be also just 3 numbers, 3 indices. So we can just rewrite introduce a connection with just one index by using a Levi-Civita symbol here. And so this achieves two things. First, that we get an SE2 connection. And so the connection has also as many degrees of freedom as the triad variable. And so that is something special for 3D. Now the connection can be conjugated to the triad variable. In 4 dimensions, that is unfortunately not the case. And so our conjugated variables, we will come later to that, will be the connection variable and the triad. Having the connection, one can compute the curvature. So that is either GR or lattice gauge theory, or sorry, Young-Mills theory. So that is similar to Young-Mills theory or first order general relativity. So that would be the curvature. As we know, we can always tie omega, the connection, to a triad. So if you do that with a matrix, you get the Levi-Civita connection. If you do that on the level of the triad, it's known as a spin connection. And so the equation which ties it together would be that the covariant derivative of the triads is vanishing. And so the covariant derivative here, you have one term which comes from the internal index with an omega, and you have one term which comes from the spacetime index, which comes with the gamma, so the Levi-Civita connection, and this has to be 0. So, well, you have in general this equation, but if if antisymmetry of omega holds, then you only need to demand that torsion vanishes. And so the torsion is defined in this equation. So it's kind of the, you see, some antisymmetrization of the covariant derivatives on omega. And finally, we can rewrite the the Einstein-Hilbert action into the triad and the connection variables. And what we obtain is a so-called first-order Palatini action. So first order because it only involved first-order derivatives, and these only appear in F derivatives on the omegas. And yeah, so in particular, this action is very peculiar. Just let me notice that. So epsilon is a constant tensor, it's not a variable. F only appears, is only a function of omega. It's the highest, the highest order in omega is 2, so it's here we have a quadratic term, but otherwise the action is linear in the triad field. So that is very, that has a peculiar significance. Because for the equation of motion, okay, you can vary with respect to omega. This is a bit slightly more involved because we have some term which is quadratic in omega here. But if you vary with respect to omega, you get the simple equation that torsion has to be 0. But if you vary with respect to E, you see that E only appears linear in this action. So what we do get is that the curvature vanishes. So we get that curvature has also to vanish. So the equations of motion and 3D gravity are very simple. And in fact, well, I've done that in this Palatini formulation, but you get the same equation of motion in Einstein-Hilbert. So that second order torsion freeness would be automatically implied because, well, you work with you already define the Levi-Civita action, the Levi-Civita connection and the Einstein-Hilbert action. And so in 3D Einstein-Hilbert, if you do vary the action, you get basically the same equation of motion as in 4D, which is that the Ricci tensor vanishes. But in 3D, vanishing of the Ricci tensor does imply the vanishing of the Riemann tensor. And that comes again from counting the number of of the degrees of freedom in these tensors. And so you get actually in both cases that these have only 6 degrees of freedom. So so these are very simple degrees of freedom. Curvature is 0, torsion is 0. In fact, what happens is in this case that we say 3D gravity is a topological field theory. So it's a field theory because in principle we have either the matrix, the 3D matrix as a field variable, or in our case, the triad and the connection. But all the degrees of freedom we have are eaten up by gauge symmetries. So in 3D, well, for the matrix, for the matrix formalism, we just have a diffeomorphism symmetry. And for the triad formulation, we have diffeomorphism symmetry and this additional gauge symmetry or rotation symmetry. And so canonically, if you would do a 2+1 split, which we do in a minute, we can count also the degrees of freedom and the physical degrees of freedom, and we will get 0. Okay, any questions so far? Or was it not sure that was known or not known? Okay, so these are the covariant equations. The covariant dynamics of 3D gravity is that curvature and torsion has to vanish. And we can look at it at the canonical analysis. And I'm doing that because one thing you can, in quantization, one main approach is to do a canonical quantization. So this will tell us which variables are conjugated to each other, and so kind of to speak about Heisenberg uncertainty relations and so on. And so if we do take the action here to make a canonical analysis, what we have to do is usually to split space-time into space and time. And so to do that, I will consider this index mu to run from 0 to 2. And also traditionally, omega is not called omega anymore, but a. So that's just a little thing which is just tradition. And so if you write that out, separating the 0 indices from the spatial indices, you get these lengthy expressions. Here's just you did just an integration by parts. And these tilde epsilons are just the Levi-Civita densities in 2 dimensions, the spatial Levi-Civita densities. As we see in the triads, variables only appear linearly. And then we also see here, if we look at the 0 component, that also just multiplies a term and only appears linearly in the action. So that's what we call a Lagrange multiplier. So Lagrange multipliers are variables which only appear to linearly in the action. And we see that this is the case for E0J and A0J and E0J and A0J. Whereas this term, that would be this, that is, you can read is a spatial part of the triads times the time derivative of the connection. So this part is very, very similar to P dot x. So that's the usual kinetic part you have in a first order action. Then you have something multiplied by a Lagrange multiplier, and then something multiplied by a Lagrange multiplier. So in the canonical analysis, you first, determine the variables which are conjugated to your variables you started with. And for that, you take the derivative with respect to the first time derivative of your variables. So the first one would be the time derivative of your connection that appears only in this term. And you see that this is conjugated to like the triad contracted with this 2D Levi-Civita. And so basically it's something from the triad variable, and we call this electrical flux. We call it electrical flux because that's also what appears in Young-Mills theory, where it is an electrical flux, or even the Maxwell theory, where it really is just the electrical field if you would not have this internal index. So we have this information now that this electrical flux is conjugated to the connection. And if you do the same game with a kind of electric flux or with a triad, we again get this information that is conjugated to that this pair is conjugated to each other. If you consider the variation with respect to E0J, well, then we get this equation of motion, namely that this curvature has to vanish. So all the spatial components of the curvature have to vanish. So AB just runs from 1 to 2, and this is antisymmetric, so it's only one component here. Or one component is in the spatial indices, but 3 components in the internal indices. So basically that is that demands flatness, so that's why it's called flatness constraint. And the other equation of motion is that the spatial components of the torsion have to vanish. Again, it's just one component, since the torsion is also antisymmetric. And so this is a so-called Gauss constraint. And so we have we have these 2 sets of constraints. So overall, these are 6 equations of motion, which J runs from 1 to 3 still. We have 6 equations of motion, Gauss constraint, and flatness constraint. In fact, the flatness constraints would correspond to what we usually call the Wheeler-DeWitt equation in 3D and 4D. So we have these 6 constraints. Also, we have these variables which we have given are these electrical fluxes and the conjugated connection. And so if you do accounting, we do that spontaneously. So the electrical fluxes here, A runs from 1 to 2, J runs from 1 to 3. So this gives us overall 6 component. Then the connection is the same. So we have a 12. The phase space dimension is 12. But here we have also constraints. So six constraints. These constraints will be what we call first class. So we get 6 equations which say that we have to restrict to the constraint hypersurface where these constraints vanish. And we reduce by another 6 degrees of freedom because, as it turns out, these constraints, they Poisson generate gauge transformations. And so they will also generate gauge transformations in 6 directions. And so if we consider like what is left over after we do that, we get a 0-dimensional phase space. And so in fact, 0 dimensions per spacetime points. So only degrees of freedom which are left over are so-called topological degrees of freedom. So this is a finite number of degrees of freedom depending on the topology of your spacetime. So for torus, I think it's 2 dimensions, two-dimensional phase space, or 4-dimensional phase space. But there's no field degree of freedom left, which is physical. And that's the main reason why gravity in 3D is much simpler than in 4 dimensions. In 4 dimensions, we would have been left with a physical phase space, which is 4-dimensional per spatial point. So it's a graviton degree of freedom, and it's conjugated degree of freedom per spatial point. Okay. And so if you do rewrite the action in Hamiltonian terms, then it's this conjugated pair, so like P(x dot) times these Lagrange multipliers times the constraints. And so this is these 2 terms we would call the Hamiltonian, but the Hamiltonian is totally constrained to vanish, so that's also the case in 4D. So the total energy in a compact spacetime or a compact space has to vanish. So that is a general result in GR. So to summarize our classical theory, we can formulate it in these the canonical theory in these variables, which are the triads or the spatial the triad variables and the connection. the action is a bit special because it's just linear in the triad variables. That's the equation of motion, which just demands that curvature and torsion vanishes. And if you just go to canonical analysis, then the constraints just appear as a restriction of our equations of motion to the spatial hypersurface. And the point is that these components of the equation of motion do not contain any time derivatives. So therefore, they are called constraints because they are constraints on our usual, or they do not contain any second order time derivatives. They are usually constraining as initial data. So if we go to the first order formulation, then these constraints would be really constraints on the phase space. And what we call proper equations of motion would involve like a time derivative of either the configuration variables or the momenta. And so the Hamiltonian is a combination of the constraints. And so that's usually the case in all kinds of, series with diffeomorphism symmetry. Okay, so that concludes what I wanted to say about the classical theory. Any questions so far? Okay, so that's not the case. Let's go on to quantization. So we start with, or let's consider this first order action. And so this is given by the integral over the triads times the curvature. The curvature, if you use first order, is just a function of the omegas. So as I said, the triads only appear linearly in the action. So if you write the path integral here with this action, we would integrate over both the triads and the connection. But if you have basically an integral which over the connection, over the triads or over some variable which just appears linearly here, like so if you have exponential x multiplying something, a function of p, then this would just act as a delta function on f of p. So similarly, if we integrate out here the connection variable, it does act as a Lagrange multiplier. So we obtain the delta function of whatever multiplies the Lagrange multiplier. So what we are left over after integrating out the triads is an integral over the connections with these delta functions on the curvature. So integral over flat connections. It's a kind of modulo space of flat connections. So of course, if I write here delta function, so that would be delta function over all space-time points. So the continuum is you have to regular. Well, it's a bit harder to define. One way to deal with that is to use a regularization, and we go to a lattice. Later on, this lattice for geometric interpretation is good if it's dual to a triangulation. And so to regularize all these expressions on a lattice, well, we can do it in a naive way, but let's do it in a nice way so that we get a nice behavior under these various gauge symmetries. And so the result will be actually very similar to lattice gauge theory. So if you know lattice gauge theory, it will be, you should be able to straightforwardly follow. So to express the curvature on the lattice, what we form is, we will form so-called holonomies. So the holonomies just do the parallel transport over finite distances. So, and these finite distances will be basically the length of the lattice. Well, to that end, we form these Lie algebra valued connections. So we could have already kind of introduced them. So that means your connections, if you multiply them with these matrices, become non-commutative. And so that is just an important point. If you form these holonomies, which is the integrated parallel transport, if you have these matrices, you need to introduce a path ordering. So this is a path ordering. And you can formally construct your holonomies, which, yeah, as I said, would in the end just provide you with a parallel transport over a finite distance. And this finite distance is as path gamma. And that allows you to parallel transport vectors. Once you have the parallel transport, then the curvature is basically measures the failure to get back to the identity once you go around a closed path. And this failure to get the identity is approximated by the integral over the curvature of the surface enclosed by the path. Of course, you can fill it with different surfaces, but you can show that this does not matter to the lowest order. So the holonomy in the end around a closed curve provides you a measure for the curvature integrated over these surfaces. And so if you do want to approximate these delta functions over the curvature at a given point, we form small closed paths and demand that the holonomies along these closed paths all vanish. And so that would define us a path integral over flat connections in a regularized way. It's still not finite because if you write lots of these delta functions, what will generically happen is that these delta functions overlap. And you can precisely kind of specify to which degrees they overlap. But actually this overlapping issue and the resulting divergences will be related to the same divergences which come from the diffeomorphism symmetry. So I will comment on these things later. So removing delta functions here is actually equivalent to gauge fixing the diffeomorphism symmetry. Yeah, so this would be the path integral in these group variables. You know, if you have a smallish lattice, you can kind of in principle figure out explicitly, or you can calculate these things explicitly. But these group variables, well, I mean, they have some geometric information. It's a parallel transport. It's a Levi-Civita connection. But on the other hand, the metric is encoded in the conjugated variable. So let's rewrite this path integral so that we have it as a integral over the conjugated variable, over something which provides us directly metric information. I think at this point it will not be obvious that this is metric information, but at some point we will see that this is actually J will be metric information. And so on a purely mathematical level, what we are going to use is a generalization of the Fourier transform. So what is called is a group Fourier transform for, in that case, compact Lie groups. There's a beautiful theory behind it, and the theorem you use is a Peter-Weil theorem. And it's a generalization of a Fourier transform in the following sense. that basically, if you look just at R, then you can understand R as a group of translations, and a representation, a unitary representation of the group of translations, is actually provided by the functions exponential IPX. So these representations are one-dimensional, and they're labeled by P. We could say the momentum, and the matrix element of this representations are exponential IPX. And so if you compose two translations, well, that would be you translate by x1 and then by x2. In fact, you can see that this multiplies the representations exponential IPX times x1 times exponential IPX2 gives you exponential IP x1 plus x2. So similarly, basically for like a three-dimensional group like SU2 or these compact Lie groups, it turns out if you're looking for a basis of functions on this group, in the function space L2 functions over this group, with a H measure, which I believe I possibly forgot here to write. There's a H measure dg here. So it's a particular nice measure on the group, which behaves nicely with respect to the group transformations. And then this basis is provided by the matrix elements of all sets of unitary irreducible representations. For SE2, these are given by, well, the spin representations or representations with spin j. And you have these indices m and n, which run from minus j to plus j in integers, in integer steps. And then normalization, there's just some normalization which applies here, which is the dimension of this representation, which is 2j plus 1. So this gives you an orthonormal basis of your space of functions on the group. So the equivalent of the Fourier transform would be if you consider basically the components of a given wave or function of the group psi g with respect to these matrix elements. And so these matrix elements have three labels. J is the representation labels, and m and n are just the matrix labels inside this representation. So a function in the group can be encoded in a function in a set of discrete elements, JMN. So I mentioned that with the translation, it's a generalization of the translation group. Even better would be the group of rotations in 1D. If you take the rotations in 1D, that would be just S1. In that case, the labels would be just one label, and that would be just n. So because then you get just n being in that being an integer number. So in that case, it's j is a positive integer, and m and n running from minus j to plus j. And so these additional indices come from dealing with a non-abelian group, which has higher dimensional representations. Okay, so we have this transform. We can transform functions on the group in this psi tilde JMN. On the other hand, we can also reconstruct our function on the group from this psi tilde JMN. Well, and that is just the equivalent of switching from the X representation to the P representation in standard quantum mechanics. So whatever you call X, so typically we call G as a configuration variable. We go from the X representation to the P representation and vice versa. So it's just a higher dimensional representation of this fact. a particular example of this rewriting, is kind of rewriting the delta function on the group as a sum over these matrix elements, and the sum appears in two different ways. We have a sum over all representation labels. And then we have a sum over all the matrix elements M and N here by taking the trace of these matrix elements. So trace means you have the sum over, so I can write it as a sum over M, and here I would write MM. So M needs to be equal to this other index N. Okay, and that gives me the representation of the delta function. You can make a simple check. The delta function is invariant under conjugation. So if I write hg, h minus 1 here, instead of just g, that would give me, again, the same thing as delta g. And this invariance under conjugation is indeed implemented by taking the trace here. And again, that is the same thing as writing the delta function over x as an integral over all piece of exponential IPX. So that would be the same thing for the analogous object for the translation group. Okay. So we had this nice integral. Very nice being because it's just an integral over a bunch of delta functions. And so this would be in principle easy to solve. But now we rewrite that into different variables and get something more complicated. Okay, and so, well, the way to do it is to using this identity of rewriting the delta function as the sum over these traces. These traces are also called characters, so as the sum over these characters. So we use these identities we obtain here. For each delta function, we rewrite it as a sum over characters. Then we rewrite these characters out explicitly as a sum over these matrix elements. And the G's, which were the holonomies along closed curves, we rewrite out in terms of these original group elements. So the closed curve holonomies are products of these holonomies over links. I think I had this picture here, so that would be the closed holonomy would be the product of H1 times H2, H3 times H4. So we integrate out these group elements. And what we would be left with this is a sum over representation labels J. And so what you use is actually some identities because these elements HL will appear in different delta functions. And so what you use is just certain identities of integrals over a number of, if you integrate H of a certain polynomial function of H, you can use certain identities, you use them. And this will be all representation theoretic because all these group elements appear in matrix elements. And so we're left with a representation theoretic object. And I just give you the result. So what you get, as I said, since you integrated out all the group elements, you're just left with a sum over these representation labels J. And this sum has a following form. The main object here would be the product over all tetrahedra in your triangulations. So remember that we were saying we are choosing a lattice, but this lattice should be a dual lattice to a triangulation. So for each tetrahedron, it's a 3D triangulation. So it's made out of gluing tetrahedrons together. And so for each tetrahedron in this triangulation, you get this representation theoretic object, which is known as 6J symbol, which you might have encountered in the theory of angular momenta. So these 6J symbols, as the name suggests, labeled by 6 spins, so J values, representation labels. And these 6 spins actually label the 6 edges of a tetrahedron. And indeed, in this quantum geometric interpretation, they do end up to give us the length of the edges of the tetrahedron. So, and that will be the main object here. So in some sense, each tetrahedron comes with an amplitude, which is a 6J symbol. So it's a number which depends on these 6 entries. For each triangle, we have a phase, which is just this -1 times to the power of these representation labels. And also for each edge, we have a weight, again, just a -1 and dimension factors. And then the partition function, so this is the same partition function, would be given by summing over all representation labels associated to the edges of the triangulation. And so here we had here we had something relatively simple because it was integral over a bunch of delta functions. It's possibly a bit harder to evaluate than you would expect naively. Here we seem to have something which seems to be hard to compute, but in fact there's certain nice properties which make it easier to compute than it would look like. On the other hand, yeah, so it has a structure which is not obvious that you can evaluate it at all. It's a discrete sum because the j's are just integers and half integers. And so this would be the partition function for quantum gravity in 3 dimensions. Okay. So we have now expressed our partition function in a somewhat complicated form. And you could ask, why did we do that? And in fact, it has some nice properties which come from dealing with this topological field theory or having this diffeomorphism symmetry. So actually, we in the beginning, for defining this path integral, we chose a lattice. And I've said it's dual to triangulation, but you could have asked, which lattice should we choose? Does the result depend on the lattice? And so, yeah, in usual lattice field theory, and if you put like QCD or Young-Mills on a lattice, like the choice of lattice will make a difference. You can consider refinements of the lattice, you will get different results. But in this case, and also because we chose the specific way to regularize path integral, and the choice of triangulation or the choice of lattice does not matter. As long as a lattice captures the right topology, which is kind of easy to make sure of. And so what it means actually that if you choose another lattice, there's a bunch of identities which tells you that the result is independent of a lattice modulo issues which come from the diffeomorphism symmetry. That is one fact. another is that there's a explicit realization of this diffeomorphic symmetry, and this explicit realization is in fact related to this invariance under changes of the triangulation. And so let's consider a particular case, a particular simple triangulation. In this case, it's a triangulation where we just have one tetrahedron, which is subdivided into 4 different tetrahedra. So we can take the black edges here as boundary edges, which we do not sum over, and the blue or green edges here as als bulk edges, which we should sum over. But then there are different bulk configurations here. In particular, if you're classically inclined, if you look at it classically, we considered that the solutions should be flat. So if you just construct this triangulation by subdividing this flat tetrahedron, you can do so by placing the vertex inside the tetrahedron. So you can choose any point inside the tetrahedron and you will get a flat solution. And so that means that you have a gauge symmetry. In fact, this gauge symmetry is a remnant of diffeomorphic symmetry. You can put this vertex anywhere as long as this entire triangulation is flat. I told you can put it inside the tetrahedron, but in fact you can also put it outside the tetrahedron. And this has something to do that we sum over orientations. So that comes from using the triad formalism, where the triads can have easily two orientations. And so the orientation, a positive orientation, comes from having a positive determinant for the matrix, defining the triads, and a negative orientation from having a negative determinant. And that fact actually allows you to even move this vertex outside of your tetrahedron so that your gauge symmetry becomes non-compact. So it's really an R3 gauge symmetry. So that means if you would actually sum over all these inner edges, you get, in fact, at least an infinity to the power of 3, so R to the 3. But how to deal with that would be to gauge fix 3 of the 4 inner edges, and that can be done precisely, and you can evaluate this R's integral without getting an infinity. We had another symmetry which was related to internal rotations. But in fact, this is a compact rotation group, so that does not lead to infinities. And so these infinities, in fact, as I previously mentioned, they also appear in this form of the integral where we integrate over the holonomies. But in this case, they're hidden in this issue that if we have delta x times delta x, that gives you an infinity, so it's kind of overlapping delta functions. So these infinities appear in the fact that these delta functions can be overlapping. And so we have these two different representations of the partition function. Sorry. Yeah, also quantum mechanically, this partition function, kind of localizes like the connection to be flat. So it's really a delta function. So delta function means that we sharply impose these delta functions. And so that would be having like, if you have a wave function, which is like delta x, we know that in the momentum variable, the momentum would be infinitely spread out. And so that, in fact, that is also the case here. Here we impose sharply that the curvature vanishes. And here, in some sense, we write in the path integral as a sum over j's. And more or less, this is the maximal spread out sum over j's, which we can achieve, implementing kind of gauge invariance and diffeomorphic symmetry. So the j's, they're positive integers, but they can get infinite large. And so it's an unrestricted sum over j's, which are the length of edges, as I mentioned. So it's not very obvious, but even if you just look at this case of a subdivided tetrahedron, these three blue edges, they can become arbitrarily large. So if you make them arbitrarily large, it's not a flat triangulation anymore, but you can make them arbitrarily large. And so these configurations are known as spikes. And so we represent this sum, which is over flat connections, however, with the sum over j's, where the j's can become arbitrarily large, particular. So what it means, you have arbitrarily large lengths. Also, these black edges can be very small. So you can have kind of infinite volume inside a region which has a very small area. So we have a highly fluctuating geometry. And it's a kind of maximally fluctuating in the sense that it's dual to something which is maximally restricted in terms of the conjugated variable. Maximally restricted because here you impose delta functions. And so this is one specific property of quantum gravity, also appears 4D. You have a highly fluctuating geometry in the sense that you have to integrate over these spikes, for instance. In Lorentzian geometry, we have also spines, so that is kind of where inner bulk edges can become arbitrarily large without having an inner vertex. And these configurations are inside regions which can have very small area, or in 4 dimensions very small 3 volume. Okay. So another sign that this has something to do geometrically with quantum geometry, and also shed some light on this issue of orientation I mentioned, is the following fact. I told you that the partition function is basically summing over these amplitudes, and the amplitude is mainly the 6J symbol. Should have said that. No, and the 6J symbol, it's interesting when it was suggested. So this was suggested as a model of quantum gravity in the 60s. I think it was 68, the publication by Ponzano-Regge. And the main argument was to say that this has something to do with quantum gravity, had something to do with the behavior of these 6J symbols for large J. And that's where, in fact, you do get an interpretation in terms of the geometry of this tetrahedron if you identify these J's with the length of the edges of this tetrahedron. And the asymptotic is as follows. So if you have these 6 J's, so you have 6 J's terms in terms of large J, and large J means, well, it's large J compared to H bar. So you could also say in terms of H bar going to 0. So it's a kind of classical or semi-classical limit. This 6J symbol gives you basically the exponential of the Regge action with an I here. The Regge action the Regge action does give you, it's a discretization of the action of the Einstein-Hilbert action. It's very geometrical for the tetrahedron. So it's just given for the tetrahedron just the length of these edges times the dihedral angle between these planes, between the triangles meeting at an edge, and you sum over the 6 edges. In fact, that gives you exactly what you would get as an Einstein, if you would evaluate the Einstein-Hilbert action for a flat tetrahedron. So what you also get is another term. So it's actually exponential I times the Regge action plus exponential minus I the Regge action. So, and this sum you can understand as a sum over the orientation, like positive and negative of the tetrahedron. And that's why I mentioned that they're positive and negative orientations. And you can understand this as coming from of using the triad variables, which can have negative and positive orientation. And so here you indeed sum over positive and negative orientation. And indeed, you should expect that because you use the triad variables as Lagrange multipliers. You know, we have seen that these impose the delta function. But to get the delta function, well, you need to kind of integrate over positive and negative orientation. Okay, so well, as we have also, as I explained on the previous slide, this negative and positive orientation leads to a diffeomorphism symmetry where you can also move these vertices outside the tetrahedron. And so it appears in this context. So this would be the leading order. So really H bar going to 0. If you want to get a correction of order square root of H bar, so one loop correction, that would basically give you the measure terms. But these can be also determined, and these also turn out to come correctly out of the semi-classical analysis. And these would be also geometric expressions in terms of the classical volume of these tetrahedron. So you do get kind of, even if you use these more abstract techniques of SU2, you do get the same result as you would if you would start with a more naive quantization using this approach known as Regge gravity. And you can read about this in these papers. Okay, here's a very short summary about the 3-dimensional path integral. And that is based of rewriting a 3D action in terms of this Palatini action, which is kind of given by the triads and the connection. And the advantage of doing that is that the action is then linear in the triad variables, so you can formally integrate out the triad variables and get a path integral over flat connections. This path integral over flat connections is kind of easy to regularize on a lattice. And the path integral over flat connections, you always get something topological. So you get only something which depends on the topology of the manifold. And that means you can typically capture this information in a discretization. So here on a lattice. So you have the path integral over flat connections. If you revise that in more geometric variables, namely the length of the edges, so metric information, you can do that technically via group Fourier transform. And it ends up to be a sum over discrete labels. The discrete labels are representation labels of AC2. They label the edges. They have the geometric interpretation of length of the edges. But technically, it's these amplitudes you have to sum over. In the end, everything is consistent, because if you look at this amplitude in the semi-classical limit, you do get a geometric result, which tells you that you do get again back the Regge action, which is a discretization of the Einstein-Hilbert action. And the Einstein-Hilbert action, well, this is equivalent to the Einstein-Hilbert action. So it's a consistent cycle that you get here. And so you could say you get, this provides you the path integral for 3D gravity. And as I mentioned, it does nicely implement diffeomorphism symmetry, and it's also invariant under your choice of triangulation. And in fact, you can argue that this invariance under choice of triangulation is equivalent to having a notion of diffeomorphism symmetry. So in 4 dimensions, if you choose discretizations and so on, this choice of discretization, well, the discretization usually leads to big problems because it does break in 4 dimensions diffeomorphism symmetry. Then you have these technical issues of having to do a continuum limit, which is hard to do because it's much harder to compute in 4D than in 3D, because the amplitudes are not just delta functions, but far more complicated. But here in 3D, we do not have these issues. We have this representation of the diffeomorphism symmetry. I mentioned that this is connected with summing over orientations. And so you could say to some degree that is one of the open questions in 3D gravity. So I also discussed here Euclidean signature. I mentioned you can do the Lorentzian signature, but there's even more questions about Lorentzian signature. And these have to do with the question whether your path integral should include degenerate triads or not. And if you do not include degenerate triads, which means where the determinant of your triad matrix is 0, then there might be also no reason to include negative oriented triads. But if you do that, we change the properties of the theory indeed. And as far as I know, we do not have any definition of the path integral where we would sum only over positive triads, but which would still have, still be like triangulation invariants or have a notion of diffeomorphism symmetry in the same way. But this is one of the open questions. It was basically something which Witten criticized his own work. So first he had a paper which basically was using a similar presentation of 3D gravity in the sense that use an action linear in the triads, but you could question indeed whether you do sum over degenerate triads or not. Okay. So this was a path integral quantization, or often it's called covariant quantization. Let me delve a tiny bit more into the canonical formulation, which gives you a bit more interpretation and connects to things which you might have seen in 4 dimensions. Or not, so that this canonical quantization and the notion of physical wave function. So here what we can consider is, again, going back to a canonical formulation, we could consider what is the wave function associated to the tetrahedron if we consider the surface of the tetrahedron as an equal time surface. And so in that case, so we we had the holonomies as variables. So we would consider wave function of 6 holonomies because the tetrahedron has 6 edges. But if you look at the dual links have also 6 edges. So in principle, the class of wave function you would consider would be a wave function of 6 group elements. When we discussed this classical theory, we had these constraints. And part of the constraints, that there was these torsion vanishes, and we call these Gauss constraints. And the other class of constraints were the flatness constraints. And the flatness constraints are imposing flatness. But in terms of holonomies, we already discussed that this should be then delta functions of the holonomies. So here I wrote this now the physical wave function, which satisfies all the constraints. So let me just start to say that these satisfy indeed all the flatness constraints. So a tetrahedron, here you can see the tetrahedron or the dual tetrahedron as looking from the tetrahedron from above. It has in principle, it has 4 triangles or 4 dual triangles. So here you see 3 of them. And here I've written only delta functions for the 3 triangles, but not for the 4th one, which would be on the other side. But this is one example where you have overlapping delta functions if you would write the 4th delta function. Because if you impose that all these 3 holonomies, which basically, I guess, I have imposed here, are flat, and in fact, you can trace your holonomies, the combination of these holonomies out. You see that this automatically imposes that the holonomy around the 4th phase is also flat. And so you do not need to impose the last delta function explicitly. In fact, if I would write it, it would define something which is infinity. And so actually this relation, like this imposing flatness, that's actually the Bianchi identity. It's a discrete version of or the integrated version of the Bianchi identity. Or of the principle that the boundary of the boundary is 0. Because here you take all the boundaries of the phase and you glue that together, and you are left with kind of no boundary at all. So this wave function does satisfy all the flatness constraints, but it also satisfies all the Gauss constraints. The Gauss constraints would just generate H transformations. So in terms of holonomies, this would be conjugation here at one end of these group elements. So if A would be group element, gauge group transformation, it would be the transformation would be A, H, A minus 1, and so on. But the delta functions are invariant under this conjugation. So, well, yeah, so this would satisfy all the constraints and this wave function. So what we usually would call it's a solution of the Wheeler-DeWitt equation and so on. And this, again, 3D is very special that we can just write down these solutions. Yeah. And again, this would be just in the like you could say, the Schrödinger representation, or in the representation where we use the holonomies as variable. We could go to the momentum representation, meaning we use the representation labels. These matrix elements inside a given representation do not appear because of gauge invariance. And if we would make this transformation, what we would find is that now we have the representation labels labeling the edges of this tetrahedron. And we would find again the 6J symbol, and then there is kind of just these weight factors, which is just the product of all these representations. Well, actually, I think it might be the dimensions, sorry, and not the representation labels itself. And in fact, this is nice because we can loop back again to the path integral. because these are the physical wave functions for a given tetrahedron, and we can glue them back together, and with the right phases and so on, you go back to the representation of the path integral. And so this is a property which we also expect in 4D. For any kind of region, we expect an amplitude. And if we glue these amplitudes back together for this region, we expect kind of like the amplitude for a bigger region. But this would be kind of the path integral. And so again, there's a consistency between canonical quantization and the path integral quantization. So the path integral, yeah. So typically you might have heard if the path integral in this case that we have constraints is supposed to project onto constraints wave functions. And indeed, this is kind of automatically implemented in this case in 3D. Okay. So that might be pretty much the last part. So I mentioned before that we can interpret the J's as lengths of the edges. And the main motivation, I think, comes from the semi-classical limit of these 6J symbols. There's a more direct quantization where you do get, you can construct the quantized length operator. So that you would get in canonical quantization. And so here, well, this, as I mentioned, for the path integral, we have a basis of wave functions given by the matrix group elements over for each link. So wave functions over the group carry bases which are given by the matrix elements. If you want to quantize the length operator, let's do that in this discrete formalism where we would try to construct something like the length operator for a link or for an edge. And for that, you would take the triad variable, which is hidden here. So there's a bit of notation here. Gamma star would be the edge. So you would integrate this triad variable over the edge, so you contract it with a tangent vector to the edge. This is this gamma star dot. But also to ensure gauge invariance, you have to transport these triads with the holonomy, because it's a vector with respect to the internal gauge transformations. So these are just these h-1 and h, so we can often these are ignored, so we can ignore that. But this kind of does construct something which you could say this is kind of a vector representing the edge of a tetrahedron. And it's quantized in the following way that these vectors, they act on the space of wave functions in G. There's a very nice phase space you consider here is actually the cotangent space of the group. And the cotangent space of a compact Lie group has a very nice quantization, which kind of says that the cotangent parts, so the Lie derivatives here, well, that these cotangent vectors are quantized as Lie derivatives, in fact. And so formally it's that the triad variable, this flux operator, is quantized as acting as a Lie derivative on this matrix element. if you write it out and write down how the Lie derivative acts as on a matrix elements, well, because the matrix elements are giving you a nice basis, it does act by just multiplying the matrix element by the representation matrix evaluated on a Lie algebra basis element. So Tk would be the Lie algebra element associated to the label K. So if you take the square of these fluxes, also to an edge, you get basically the square of these operators. So these operators, in the end, you might be reminded of the angular momentum. In fact, it's exactly angular momentum quantization. So this, if you take the E, so that would be similar to JK. That gives you the Casimir of SE2, and that has a discrete spectrum for the length square operator. It's just J plus 1. And here I have the 3D Planck length. And this gives you a quantization of the length operator, and you see that you get J plus 1. So the length itself would be proportional to square root of J plus 1, which is approximated, particular for larger J by J. So that's why you can identify J with the length. And now you have, again, this interpretation of the Ponzano-Regge sum as a sum over discrete lengths of your triangulation. And so in this sense, it's a sum over geometries. And so this is a picture of quantum spacetime you get here. So first, it's not kind of a smooth manifold anymore. It's a quantum. Well, it's a quantum manifold in the sense it's represented by this path integral where you sum over all lengths of your triangulation. And furthermore, these lengths, in that case, that you have Euclidean signature, can only take discrete values. And so that gives you the quantization in 3D gravity with these certain caveats I mentioned. And these caveats, again, were related to whether you should include degenerate triads in the path integral, and that related to that, whether you should sum over orientations. Okay, actually that brings me to the end of the lectures, I believe. Yeah. So these were the basics of one approach of 3D gravity. So that is mostly representing the Ponzano-Regge model, that is the path integral, which then relates to canonical quantization. So you get a quite complete picture. You might have heard in 3D gravity, you can quantize via Chern-Simons theory. It's very near to what I presented here. So the first order action and the formulation I've presented here, it's equivalent to the Chern-Simons quantization. So Chern-Simons is also topological theory in 3D, where you, to some extent, work more directly with the topological theory. And you can show that, if you take care of all these gauge symmetries and so on, it's actually equivalent to Chern-Simons. Well, as I mentioned, these Psi lecture notes where, in fact, I do concentrate on 3D because it gives you a nice toy example to understand all the puzzles people have in 4 dimensions. 3D, you can do a lot of stuff. The path integral, you can kind of solve it to a certain degree. And we have used that to derive holography. So it's not postulated, or it often is, but we start from the 3D path integral and then derive the boundary theory. And again, 3D is special here, so we don't need EDS CFT. In fact, we do that for the flat case, so for having no cosmological constant. And also, we don't need to go to infinity at all. You can take any finite boundary and get a boundary theory, which just encodes your choice of boundary values. So you can read that in these papers, where I think this one is a summary of the other two papers. If you choose your boundary data specifically, you get a representation of the BMS group, which is interesting. It's an asymptotic group. It's interesting in this case because usually you would associate that to the Lorentzian case, but we actually do this calculation locally here. And here's also a paper more specifically about the Ponzano-Regge models, which introduces the Ponzano-Regge model, gives you the correct phases and so on, which is not often done in the literature, and concentrates more on certain topological aspects of using the Ponzano-Regge model. In fact, so this Ponzano-Regge model is for the flat case. It's inside a family of models. The more general models are Turai-Viro model, in which you replace SU2 with a quantum group SU2K. And these quantum group models, well, they have become very popular, like maybe 20 years ago in condensed matter, under the name of topological phases. So in fact, all these condensed matter theory about topological phases, well, they've done basically quantum gravity, but the theory is the same theory. And previously, the Turai-Viro model was defined as a topological model, which is also related to knot invariance and so on. So there's a lot of mathematical theory behind these constructions, which I didn't mention here.